Cauchy's residue theorem. While Cauchy's integral formula offers a straightforward way of evaluating integrals along contours enclosing regions containing a single pore singularity, it cannot be used if multiple singularities are present within the contour. The following theorems offer a robust alternative in this case. It means that if the contours enclosing the regions containing a single pore singularity, we will use the Cauchy's theorem. But if multiple singularities are present within the contour, so this theorem is not appropriate. We will use the residue theorem. Now I have to make sure that fz is analytic and within or on the closed curve, where this is the residue theorem. You integrate the closed curve fz is analytic with respect to dz. Then this is equal to 2 pi j multiplied with the sum means total, of the residue of the fz at the pore inside the contour C. Okay, still recall that the way we calculate the residue for single pore. Okay, residue fz z0, we take the limit, okay, where z approaching z0 for z minus z0 multiply fz. Okay, but for m order of pore, okay, we need this 1 over m minus 1 factorial. Okay, and then we take the limit when z approaching z0. Okay, so you have to perform this one first here. Okay, so you take the differentiation up to m minus 1 order. Okay, and then here is the multiple of z minus z0 power m multiply fz. Now let's refer to this figure 4.11. Okay, the integration contour enclosed points z1 and z3 but not z2. So as you can see inside the contour, and here z1 and z3, both of the poles here, they are inside the contour. Okay, except z2. Okay, z2 is outside and need to be, this is we do not need to include this in the calculation. So when you sum out, we will find the residue for the pore at this point and this point, yeah, but not this point. Then after that you sum it up and multiply it with 2 pi j. Okay, so here's the formula, or you can refer to the notes here, yeah, the sum. So you add it up, or the residue, and then you multiply with 2 pi j. Let's look at the example 4.30. It said evaluate the closed contour, okay, where C is the closed path enclosing the point z equals to -1. Okay, we work it out here. Now as you can see here, okay, the function has a pore of order 2. Okay, pore of order 2 at the singularity point with the z0, which is equals to -1. Okay, now first we have to find the residue of z at the z0, which is -1. Okay, so this is pore of order 2. Alright, so this is not the simple pore. So what we need to do is we use the formula 1 over, we use this one, which is m minus 1. Yeah, so your m is equals to 2. Yeah, so 2 minus 1, you get 1 factorial. Then you take the limit 1 over 1 factorial, this one you get 1. So z approaching -1, you differentiate up to how many times? M minus 1, so 2 minus 1, you just differentiate 1 time. So your z minus z0, okay, and then your fz, what is your fz? Exponent z over z plus 1 square. Okay, so this is equals to 1. You only take the limit when z approaching -1. Okay, this part here you cancel, so you have up to the, we have the m here, yeah, we don't mix up the m. So this is 2, okay, 2, so we cancel cancel. So what's left is only exponent z left. So you take the limit when z approaching -1, so you will get exponent -1. Okay, so this is the residue, so no check finish. For the integration or integral cross path for the exponent z, z plus 1 square dz, so this is equals to 2 pi j according to the residue theorem. Okay, 2 pi j. Okay, and then multiply with the sum of the residue of fz at the pore inside the at the pore inside the contour. So this is the only pore inside the contour. Alright, so 2 pi z multiplied with the exponent -1. Okay, let's look at another example. Okay, evaluate the contour integral where c is a, the circle, okay, the magnitude z equals 1, and b, the circle, magnitude z equals 4. Means that, okay, we have to evaluate this contour for the path c when c is a contour of the circle with the radius 1, a, b with the radius 4. Now we work it out here. Okay, now let's let the fz equals to this, yeah. So this is our fz, and also we can actually take out the common factor here, as you can see, yeah. So you take out the factor z, so you get z squared plus 4, and then also you can factorize it. Okay, so this part z squared plus 4, you factorize it, you get z plus 2j, z minus 2j. Okay, so now we know that, okay, fz has a simple pore. So we have multiple singularity here. Okay, so we have the z0 equals to 0, z0 equals to -2j, as well as z0 equals to 2j. So we have 3 singularities here. Okay, so we have to calculate the residue for each of them. Residue of fz. Okay, fz at the first one, say z0 equals to 0. Okay. Okay, so we'll take the limit when z approaching 0. Okay, so z minus 0, and then multiply with your fz. Okay, you can put down your fz here. Z cubed minus z squared plus z minus 1. Then we have z plus 2j, or z plus minus 2j. Okay, in fact you can use z squared plus 4 here, no worries. Okay, so you cancel this. Alright, so when z approaching 0, so what do you get here? You will get 4, yeah, 0, 0, 0, so -1 over 4. And we have to find the residue of fz at the second singularity, which is, say, -2j. It's still a simple pore, yeah. So z approaching -2j, and then here we have z minus z0. Z0 is -2j. So z minus, so minus negative, so we get positive here. And then your fz. Okay, so we cancel this. So you take the limit when your z approaching -2j. So you can calculate when z approaching -2j. So you work this out. Okay, in fact, this one we get negative 8 j cube. Okay, negative 8j cube. So we will get okay, so j cube is j square times j. So your j square is negative 1. Okay, so negative 8, negative 1, you get a positive 8, and then you have j. Yeah, and this one here you get 4j square. Yeah, 4j square, so you get negative 4. Okay, so you have minus negative 4, you get plus 4. Okay, and then I have minus 2j minus 1, and then this part here, yeah, for this part you have negative 2j multiplied with the negative 2, negative 2, so you get negative 4j. So I get 8 positive 8j square. Yeah, and then you know that your j square is equals to negative 1, so here you get negative 8. Alright, so you put down the real part, separate the real part and the imaginary part. So 4 minus 1, you get 3 negative 8. Yeah, and then this part 8j minus 2j, so you get 6j. Yeah, and 6j over here you get negative 8. Alright, you can simplify here, so you get 2 3 2 4. Okay, so the answer for this one is this. Okay, and then the third one, we have to find the residue at another singularity. Residue of the fz at the z0 equals to 2j. Yeah, 2j. Okay, so you can use the same method. Take the limit when z approaching 2j. So your z minus your z0, and then your fz. Then this part will be your fz. Yeah. Okay. So you take the limit when z approaching 2j, z cubed minus z squared plus z minus 1, and then you have z plus 2j. Okay, when z approaching 2j, you get 2j cubed minus 2j squared plus 2j minus 1, and then the denominator 2j plus 2j. Alright, now if you work this out here, this part, you will get negative 3 over 8 plus 3 over 4j. Okay. Okay, so we go back to the question again. He said evaluate this where C is A, the circle. Okay, the circle for magnitude Z equals to 1. Now if you draw out the circle, okay, I mean it's center at the origin, okay, with radius 1. Okay, so you can check just now your singularity. You have 0, 2j, as well as negative 2j. Alright, so this one is 0. Okay, the other one we have this one also 1. Yeah, 1 because the radius 1. Okay, the other one will be 2j. Where is your 2j? It will be up here. Yeah, so say this is 2. Okay, this is your imaginary part. This one is your real part. And negative 2j is supposed to be here. Okay, and you notice that only this is inside the contour. Okay, only this point is inside the contour. For this point, 2j, okay, 2j here, yeah, sorry, 2j here, this is not or this is outside the contour. In other words, this one also outside the contour. So the answer for the fz, I mean the integral for fz, okay, so this is equals to your 2 pi j, okay, multiply with the sum. So we only take this residue, yeah, the sum of residue, only this, but not this and this for this contour, for this circle. Okay, so we only take this, multiply it with the residue. So residue, we go back here, residue at z not equal to 0 is negative 1 over 4. So multiply with negative 1 over 4, so we get to half pi j. Okay, for B, the contour is the circle, okay, equals to 4. So that means that if you draw the circle here, that this is the circle. Okay, my circle is not that round. Imaginary part and real part. Okay, and recall that we have the singularity z0 equals 0, 2j and negative 2j. So negative 2j is here, 2j about here, and then z0 is here. So that means inside the contour for this singularity or this z0, yes, it is inside the contour. Okay, and for this z0, for this singularity, 2j, yes, is also inside the contour. For this one here, yes, it is also inside the contour. So the integral for the fz so this is equals to 2 pi j multiplied with the sum of the residue. So you need to add up, okay, add up the residue of the fz at 0 plus the residue of fz at the 2j, as well as the residue of fz at negative 2j. Okay, so you have to plus the residue for these three singularity together, and then you multiply it with 2 pi j. Okay, let's go back, trace back. Okay, so this one, okay, plus this, okay, all plus it together because three of these singularities is inside the contour, okay, for part B. Alright, so this is equals to 2 pi j if we add it up all together. So first one, then we have the second one, minus 3 over 8 plus 3 over 4j. Okay, so before you multiply, we can simplify here. This part we can cancel. Okay, and then this part, if you add it up all together, okay, you get negative 1. So the answer, you get negative 2 pi j. Okay, the working on the notes there already shows the solution for this example.